So last time we met, we discussed this, we were looking at the response of this circuit. Okay. There is RL and then the MOS transistor has a certain GDS and GM and parasitic capacitances CGS, CGD and CDB. Okay. Our output is the voltage across RL. Okay. What was the response? The DC gain is minus GM by GDS plus GL, and it has a pole and a 0. I think this is what we had got. Okay. So if either of the parasitic capacitances CGD or CDB increase, the pole moves to lower frequencies, and if CGD increases, the 0 also moves to lower frequencies. Okay. So is this it? What is unrealistic about this analysis? Is there something in real life that we are omitting in this analysis? Source resistance, yeah. So it's almost never the case that we drive it with an ideal source. This is something that we don't find. We always have some source resistance associated with it. In fact, we'll find when we go and design op amps that we will drive it with something more like a current source, not a voltage source. Okay. So what do you think happens if I introduce a source resistance? Okay, first of all, CGS was out of the picture in the original circuit, so now it will come into picture. It will become second order. 3 capacitors in a loop, 2 of them being independent. Okay, second order. And can you say something about the poles and zeros? Have you analyzed this problem before? Where? The first assignment. Yeah, that was the idea. So what's the answer? You can look back at what you've done and figure out. GDS plus GL by CDB is one pole. Okay, one of the answers is that GDS plus GL by CDB. You mean minus this. Okay, that is one pole. And what else? Pardon? Okay, so the other answer is, the other pole is 1 by RS and CGS plus, yeah, so GM by GDS plus GL times CGD, okay, something like this. How did you get this? So you multiplied CGD by the gain of the amplifier to get the Miller multiplied capacitance, added it to whatever is across RS, and then you got the answer. How did you get the first one? GDS plus GL by CDB? Yeah. What about the other capacitors? They don't come into picture? Everyone agrees with this? These two answers? I mean, maybe there's slightly off, some constants are omitted, not constant, some little bit is omitted, that's okay. But does everyone agree with this? Okay, you are saying you will have CDV plus, I will make more room for it, GDS plus GL, and the answer he gave was CDB. You are saying you will also add CGD in series with CGS. Okay, and the other pole is where ADC is the DC gain of the amplifier, that is the absolute value of the DC gain of the amplifier. Everyone agrees with this? Is this what you remember from the first assignment also? Oh, sorry, yeah, okay, this is a mistake I made. Now, what he said in fact was CGD. Okay, so this is CGD. I had written CDB, that's not CDB, CGD. Is this correct? What do you think? Now, the idea in both cases is you look at the conductance, in this case it's GS, look at the capacitance across it, it turns out to be CGS, which is directly across, plus Miller multiplied CGD, sorry. And then here you look at the conductance at the output, which is GDS plus GL, and the capacitance across it, which is this. So, is the answer correct? Which one? GS plus? You should also have GDS and GL here. Why? Effect of GM should be included. So, what is the effect? So, actually it's not just the conductive part comes from this and this as well as GM, because there is feedback from the output of the transconductance to the input. Okay, and in fact that will turn out to be the dominant part. Is this okay? So, this is not the right answer, and if you go back to what you had done earlier, this is not what you will get. Only if CDB is 0, only if CGD is 0 will you get something like this, otherwise you will not get this one. Okay. So, let us see what the answer is. Just write out the equations again. So, these are the two equations corresponding to Kirchhoff's current law at the two nodes. So, this voltage is denoted by VGS and this is still VO. Okay. So, there are two nodes, one is this and the other one is this one. So, we get this set of equations. Okay. So Vs is the input, or we can call it Vi. Okay, let me call it Vi instead. So what is V0 by Vi? What is the DC gain? What will be the DC gain of the circuit? Gm by GDS plus GL. That has not changed because the source resistance has no current flowing through it at DC. Okay. So this has no effect at DC. There is the voltage drop across RS is 0. What's the coefficient of S? What do you get? Please solve it and let me know what the coefficients are. So the numerator it's clear. The 0 will be at Gm by CGD. Okay. Sorry, this is reversed. Yeah, that's the right way to do it. So if you normalize it, this is what it turns out to be. If the DC gain is 1, right? I mean DC gain is Gm by GDS plus GL. Okay. So what is A and what is B? A I think is this. But huh? Oh yeah, there should be another. That's correct. Yeah, it should have dimensions of 1 over frequency squared, right? What is B? What is B? This has already been worked out. The idea of giving it in the first assignment was so that you can look back at it and figure out what the answer is. CGS, CGD, GS plus CGD okay. Okay, that's it. GM CGD.
Divided by GS into GS.
Yeah, I think this is correct. Okay. Just verify if this term, you also get CDB here? CDB by GL plus GDS or only CGD? It's correct, is it? It's correct. Okay. So where are the poles of the system? Huh? Yeah, I said if we assume well separated poles, we can approximate the poles to be minus 1 by B and minus B by A. Okay. Okay. So this is what we get for one of the poles. Is it close to any of the answers we had got before? As GS tends to infinity? Yeah, but we said that that part was not correct, right? GL plus GDS by CDB plus CGD. What is this? What is it? Huh? So this is actually, you can see CGS and Miller multiplied CGD, right? Is this clear or no? This is the DC gain. Okay, so this whole thing is Miller multiplied CGD. Does everyone understand this? Yes or no? So we have 1 plus DC gain times CGD plus CGS. So this is the term we had got by sort of vaguely looking at the circuit. Now there are also additional terms that come out in the exact analysis. Okay. So essentially this is the pole associated with the input conductance GS. It is if GM by GL plus GDS is very large, it is reasonable that this term dominates everything else. Okay. So in that case you will have only the part due to GS and this will go away. Okay. Is this clear? So one of the poles is, roughly speaking, GS divided by CGS plus Miller multiplied CGD. Now there are several approximations we have made. One is in obtaining the solution to the quadratic equation itself. So even this is not the exact value of the pole. Okay, we have approximated it a little bit, but it will turn out that under some conditions this will dominate the picture, and you will get the pole to be GS divided by the input capacitance, which is directly across GS plus Miller multiplied CGD. Okay. So this is what we had discussed earlier also while doing the assignment. And what is this? Minus CGD plus CDB into GDS plus GL plus GM CGD plus did you get this? Into
the denominator multiplied by the GS into GS plus
now the dimension looks correct to me. You have conductance by capacitance, right? Okay. Did everyone get this? Please work it out. I mean, if you don't work out every step, you will have problems in the quiz or even in the assignments. So please work out every step and make sure that this is the answer you get. I'll rearrange it just a little bit. I think this is what we have. Okay. So what is the saying? Sorry, the last time again I made a mistake. This is CGD. Okay. The denominator is CGS. Okay. Yeah. So that is the strategy we adopted last time also. We'll have, I'll divide both the numerator and denominator by CGS plus CGD. Okay. So this is what I'll get. Okay. And here I'll get something. Yeah. Actually, this whole thing will, yeah. So GM will get multiplied by CGD by CGS plus CGD. Okay. Which term is missing? GDS? GS times CGD. So I'll just add the GS here. Is this correct? This is what we get. So what is the interpretation of this answer?
The GM very high, we can ignore the other two term in the numerator.
Okay.
And what we say is the GM by the capacity coupling is being seen as the output, and this is a net step at the output.
Yeah. Do we get the GS CGD term here in the numerator? We do. We do get it? Okay. Okay, that's fine. So, okay, divided by CGS plus CDB plus CGS CGD by CGS plus CGD. What is the denominator? What's that? Yeah, so the denominator is nothing but CDB plus CGS in series with CGD in series with CGS. Okay. So this is what is the denominator. Now the numerator has several terms. The last term, if you look at it, it's related to GM. It's not related to any physical conductance. Okay, it's related to a transconductance. Now you get a conductance out of a transconductance if you have feedback around it. Isn't it? If I have, let's say, this is the controlling voltage Vx, and this is the control source GMVx. I connect the output to input. What do I get? A conductance of GM. Is this clear to everyone? If I apply a voltage here, a current GM times that voltage is drawn out. Okay, so it is equivalent to a conductance of GM. Now what does this represent? CGD by CGS plus CGD. So for instance, if I have, let's say, a factor alpha here, okay, and I apply a certain V test, what do I get here? Vx equals alpha times V. So this current will be what? Alpha times Gm times V. So it's equivalent to a conductance of alpha times Gm. So it's the feedback factor times the transconductance. Now here it says that alpha is CGD by CGS plus CGD. Where is that in the circuit? So if you ignoring other elements, the circuits can be drawn like this. We have GM, CGD, and then CGS, and this is GM times VGS, where VGS is the voltage across CGS. Okay. So what is the conductance I see from this side? If I apply a test voltage V, what is the voltage I get here? What is the voltage I get? V times CGD by CGS plus CGD. Okay. And that voltage times GM is drawn out. That is the conductive part. Is this okay? There is a capacitive divider around the GM in feedback, and the division ratio is CGD by CGS plus CGD. So that appears in the numerator. So at least like some part of the numerator we can have very easy explanation for. This is fine. This part, that is the feedback around GM, which gives you a conductance of GM times CGD by CGS plus CGD. What about this? What is this? That is directly across the output, right? So this is what we have. And across this whole thing we have a capacitive structure like this. So that explains why we get these terms divided by this thing. Now, this is only some sort of approximate analysis, right? You have coupling between everything and everything else. So you have these other terms also. It's not very easy to figure out how they come about, but we will have those things. Okay. So, but in the limiting case, in some cases where GM is more dominant, we can very easily see why this turns out to be the pole. And in that case, this approximation also turns out to be very good. Is it okay? Now, obviously, this whole thing breaks down if CGD equals 0. Right? If CGD equals 0, there is no feedback around the MOS transistor. So, you will certainly not get, it's not like you will get a small value of this term. You will not get anything. Okay? Should not have anything related to GM. So, the circuit we were analyzing was this. Okay. So, what are the poles with CGD equal to 0? This is an artificial case. It won't happen in a MOS transistor, but you could sort of use this as a limiting case when CGD is very small compared to certain other things. Now, what those other things are, you have to determine from the equation. Basically, when I say it is negligible, it means that that term in the Kirchhoff's current law equations is very small compared to others. Okay. What are the poles? What are the pole values? So, in this case, we have two separate first order systems, right? So, the pole associated with this part is minus 1 by RS CGS, or basically minus GS by CGS, and the other pole is what? Minus GDS plus GL by CDB. Okay. And where are the zeros? There is no zero. I mean, when CGD is 0, the 0 is at infinity. Huh? Okay. Now, if you have any extra load capacitance, which can happen quite frequently, you simply add it to CDB, isn't it? Like if you load the common source amplifier with a capacitance, in addition to a resistance, the same equations hold. You simply have to add it to the CDB, that's all. Okay. Similarly, if you have additional parasitics at the input, because of whatever reason, you will have to add it to CGS. So this will hold for, this will hold pretty generally. It's not just with the intrinsic MOS transistor. If you have extra parasitic capacitances or load capacitances, you can simply modify these equations by altering one of the terms. Okay. Now when CGD is large, let's not even worry about how much is large, but CGD is significant, let's say. Where are the poles? Where is the zero? Where is the zero? So plus GM by CGD. Where are the poles? minus GM by I didn't hear what you said. CGD multiplied by the DC gain. This is minus GM. Why? Yeah, it's when CGD is significant, the poles will be at, let's say the first pole is at GS by CGS, which appears directly across GS, plus CGD 1 plus GM by GL plus GDS. Okay, this is an approximate thing. You will get some extra terms in the equation. Okay, but when CGD is significant, it will perhaps dominantly contribute to the capacitance at the bottom. Okay. So, especially when CGD is significant and when the DC gain is relatively large can be 10 also. This is approximately the pole. Okay. And what is the second pole? So, it is GM times this capacitive ratio plus the whatever conductance you see at the output, which again may be negligible compared to GM times the capacitive ratio, divided by CDV plus CGS in series with CGD. Okay. Is this clear? So, you do the analysis, you get a second order denominator. If you try to solve the quadratic exactly, it will become too complicated. So, we resort to some approximation. But then because of that, you have to solve it and then see whether the approximation was justified or not. Okay. Because in general, a second order denominator can have real zeros, real poles, complex poles, anything. Okay. So, in this case, this approximation holds only when the poles are real and far from each other. Okay. So, we use different approximations for, let's say, small CGD and then large CGD, and then the poles will go somewhere between one and the other depending on the value of the CGD. Okay. The approximation does help us study the circuit qualitatively, but whenever you make this approximation, you have to make sure that it was justified by looking at the answers. Okay. So, for instance, if P1 came out to be, let's say, 1 megahertz corresponding to 1 megahertz and P2 is at 1.5 megahertz, then clearly the approximation was not valid. Okay. Any questions? Pardon? Yeah, let's discuss that. We'll discuss that. Okay. So, the 0 is at infinity. In this case, it is at GM by CGD. I will call this the input pole. Note that when you have CGD, you can't really separate it. GS will appear in everything, GL will also appear in everything. When you have coupling like that, you cannot really separate it as pole at the input and pole at the output. When you don't have CGD, it's very clear. There is one pole associated with RS, one pole associated with the output conductances. So, this is an approximation. So, also keep in mind that I didn't invoke Miller's theorem and come up with this. I solved the quadratic equation approximately, I got here, and then I pointed out that this is close to what we get using Miller's theorem. So don't go around using Miller's theorem indiscriminately. We'll see why in a moment. So the output pole is, without this it is at GDS plus GL by CdV, and here it's approximately equal to So what has happened to the poles with the presence of CGD? Have they moved to lower frequencies or higher frequencies? Higher frequencies. So which way have the poles moved? So P1, it's very obvious that from these expressions that it has moved to lower frequencies. The numerator is the same, the denominator has increased. And because of GM, the denominator could have increased significantly. Okay, because of GM by GDS, the DC gain and CGD. So P1 moves to lower frequencies, and P2 moves to, the numerator has increased, the denominator has increased. Which is more significant? So most likely this is going to be more significant, so it has moved to higher frequencies. Have you seen this kind of phenomenon elsewhere? Yeah, this is pole splitting, where what is CGD doing? It is introducing, before there were two uncoupled first order systems, and you have a CGD introducing coupling between them. So the poles, one of them moves to lower frequencies, the other one moves to higher frequencies. So this phenomenon is known as pole splitting. But have you seen something like this? Where? No, that is true. That is in this circuit. I mean, that is the same thing. I am saying in some other physical system. Have you seen this? What's that? I can't hear. Compensation. No, that is this, right? So in something totally different. What's that? Band splitting. That's exactly what it is. You have a single atom, you have some energy level. You have a large number of them together. Essentially, there is coupling between them. Okay, so you have split between the valence and the conduction bands with the band gap in the middle. Okay, so that's I mean, if you write the equations, it's something similar that happens. Okay. So yeah, for us this is very useful for other reasons. We want a first order type of response when we want to make a feedback amplifier. So one way is to make one of the poles at very low frequency. Now here at least we see that by introducing CGD, that is by artificially increasing the value of CGD, we can move one lower and one higher. Okay. So we will use this in compensation. I got it backwards. I think something is happening. When I say decreases, it moves to lower frequencies. Okay. So this phenomenon is known as pole splitting with increasing CGD. Okay. So, those of you who didn't follow it exactly, please go through the analysis and do it step by step, right? Don't do it because you remembered something or anything of the sort. You make sure that you understand every step and then go through the whole analysis. Make sure that this is the conclusion you draw. If you don't, then you figure out what's wrong with the analysis. Okay. Now this is something that we use widely both for, of course, first for analysis, we want to know how the common source amplifier behaves, and secondly for design. Like we said, this pole splitting phenomenon is useful for frequency compensation. So we will use it by increasing the value of CGD. I think you are already familiar with what is usually called Miller compensation. That's what that is. You put another capacitance across CGD and you emphasize this pole splitting until a point where only one pole is dominant. Remember, we discussed these feedback systems and we said that we'd like to have an integrator or essentially a first order filter with a low frequency pole, and all other poles should be beyond the unity gain frequency. Now, let's say we end up with a situation, we have an amplifier, we design a common source amplifier, and these are the poles we get. Let's say these are the poles we get. Let's say CGD is not very significant, so this is the answer. And the two poles turn out to be close to each other. So, the magnitude response may look like this. Okay. Minus 40 dB per decade. So, this is P1 and this is P2. Now, if CGD equals 0, there is no guarantee that P1 is at a lower frequency than P2, but I am just drawing it that way. Okay. So, how do you make it a first order system? So, one way is you introduce like further additional pole so that you get something like this. That is always possible, right? I can, in front of the entire amplifier, I can have another additional pole at a very low frequency so that these two will move beyond the unity gain frequency. So, this is something else I could do, but this is kind of inefficient. Instead, I could try to, if I could move one lower while simultaneously moving the other one higher, it looks like I could do something like this. Okay. What is the difference between these two? The unity gain frequency is higher in this case. So, that gives you better bandwidth. Okay. We will discuss this again in more detail, but you get the idea. If you try to make a very low frequency pole independently of these two, so that both these go below the, if I don't play around with P1 and P2, I have to place the unity gain frequency before P1. Okay. Now, if I play around with the circuit such that P1 moves to lower and P2 moves higher, I'll have to place the unity gain frequency before the modified P2, okay, which is going to be larger anyway. So, the bandwidth will be higher if you do something like that.
Sir, design will be always aims for higher bandwidth. I mean, let's say
yeah. So, do we always worry about higher bandwidth? That's a good question. So, when I say high bandwidth, maybe I should qualify it, but it's hard to do that quantitatively at this point. So, we saw vaguely that the power dissipation is associated with bandwidth. Okay. Now, the bandwidth in absolute terms may not be very high, but whatever functionality there is, I would want to achieve it in the same power or lower power. Okay. So, another way of putting it is, instead of maximizing my bandwidth, I can say that for a given bandwidth, I would like to lower the power dissipation. Okay. The same techniques apply, meaning essentially the design should not be inefficient. That is the bottom line. Okay. I should not go and make an amplifier with a very poor bandwidth whereas a higher one is possible with the same power dissipation. Okay. It is in that sense that I say we have to increase the bandwidth, but what you say is true. Sometimes you want to cut out all the high frequency noise, and sometimes in fact the challenge may be to get a low bandwidth. If you want to get a very low bandwidth, it's also very hard because bandwidth is always related to some conductance divided by some capacitance. Okay, in one way or the other, it has to be like that on a circuit. Now you have to either lower the conductance to very small values. What happens if you lower the conductance to very small values? What's that? Yeah. So one is, of course, the very small conductance means very high resistance. We may not be able to implement it. What else? The area increases. What happens to noise? So if you increase the impedance level, the noise can increase also. Or you have to increase the capacitance, and then you have the same problem. If you try to implement a very large capacitor, you will end up wasting area, which may not be possible. Okay. So sometimes that challenge is there, but for now we can sort of assume that maximizing the bandwidth at a given power dissipation is our priority. Okay. The absolute value of bandwidth we are not concerned with. It may be a 1 megahertz design, it may be a 1 gigahertz design. But whatever bandwidth there is, I would like to implement it with the lowest power dissipation. Okay. No, not always, right? If you have, like I said, when you are filtering out something, for instance, high frequency noise, you would not want the circuit to respond to that at all. Okay, that is the meaning of filtering, right? So if you have high frequency fluctuations somewhere, maybe the output should not respond to it. So let's sort of stop here, and there were questions on Miller effect, which we'll discuss tomorrow. Okay. So in the meanwhile, you can also think about why that Miller effect is not completely valid. The other day we discussed how you can split